Welcome to the lab program of the Physics Department of Queens College. This is angular motion. This is some of the equipment we used. You'll recognize most of it. A ruler and a caliper for making measurements, different levels of precision. You'll recognize the mass holder and the slotted masses, which we can pile up and add mass to, and a nearly massless string, which can be neglected in our little discussion. The other items, a black bar or the brass pieces, and that circular thing I'll discuss when I assemble the sensor. That describes the lab, lists the objections, the resources, gives an introduction of some very brief facts about angular motion, which you should know by now. And the report, you're going to use the standard report we've been using all semester. There's some mention of what the equipment is and how you should be calling it out as for uncertainty, a discussion of the uncertainty, and the two procedures. In the first procedure, we're going to maintain the moment of inertia and vary the driving force. And in the second one, we're going to maintain the driving force and change the moment of inertia. And I'm going to go to a short video on how I did that now. And here's our sensor of choice. It's a Pasco rotary motion sensor. There's a shaft and a frictionless bearing here that spins, and there's a rotary encoder that reads that information, and we can transfer that to capstone. The round thing is a pulley. The large black ring is for other purposes. There's a medium ring, and then there's a small ring. The square piece on the bottom isn't a pulley at all. It's for another purpose. We're going to be using the small ring, and I have measured that and inserted it into the Google Doc. The pulley sits on the shaft and locks in with a key. Somehow, like that. Now those other things, the shaft and the brass pieces. I'm going to insert the brass pieces on the ends of the shaft. Like that. And I'm going to attach the bar to the pulley. It locks into those pins, and it sets with a screw. And I'm also going to take the opportunity to lock in my string. And there we go. This will rotate, and we'll read the information in capstone. The question is, how do we get a driving force here? We want it to be something nice and uniform, and our go-to is gravity. So what I'll do is I'll set this up at the edge of a desk, and I'll hook a string over it. I'll wind the string up on the pulley and drop a mass here. The mass will go down through the force of gravity, will be transferred through the string, which has a negligible mass and can be ignored. The pulley is, of course, it's going to have angular motion, it's going to have friction, but they're small enough here that we're going to ignore them. And give me a second and I'll do a run for you. And here we have it. I have a mass. That's the first mass in the capstone file. I'll turn on capstone, hit record, release it. And the weight of this will accelerate the rotating platform. It will be collected in the form of angular velocity and capstone, and then you'll analyze it from there. The other way we're going to do this, procedure 2, is we're going to take these and we're going to move them in approximately 2 centimeters. And I'll measure, because it's important that we get them the same on both sides. This thing has to remain symmetrical. There. Now I've changed the moment of inertia by changing the point masses, and we'll do the same thing. I'll release it with a mass and let it spring. This time I'll keep the mass constant and change the moment of inertia, and you'll analyze it from there. And that's it. And finally, let's take a brief look at the capstone file. This is the data that you're going to find. This is the first run of procedure 1. All of the procedures are numbered. Procedure 1, trial 1, and it gives the weight that was used as the driving force in each case, up to 10. And then it tells you procedure 2, same deal. You can get any one of them by just selecting it. And to extract the data, you will use a highlighting box. You will make sure you get a lot of the data, but be careful about the ends, because it may be a little bit odd at the very bottom and the very top, where it changes direction. You'll then do a fit of the proper type and extract the data. It should be very obvious what you're getting, considering you're looking at the slope of an angular velocity over time. And then you will take it and put it into a table, and you'll complete the analysis as outlined in the Google Doc. And that's it for this week. Good luck.